We know that NTP, or Network Time Protocol, allows us to synchronize our network devices, but there's a more accurate protocol that we're going to consider in this video. It's called PTP, Precision Time Protocol. While NTP is really accurate, its goal is to provide accuracy under 10 milliseconds, but PTP, Precision Time Protocol, its goal is to provide accuracy of less than 1 microsecond. And as a result, we measure that accuracy in terms of nanoseconds. They work a bit differently. NTP has an NTP server from which clients can request time. So I might have one network device go out to my NTP server on my network and say, what time is it? And they can synchronize their time. It's a little bit different with PTP. Here we have what's called a PTP Grand Master Clock. That is the authoritative time source for a PTP domain, and it's going to periodically push time out to other PTP clocks. And you might be wondering, why do we need such precise time in the network? Well, we don't always need that level of precision. NTP is still great for synchronizing time with network clients like PCs, doing network monitoring and checking logs. It's great for Internet of Things or IoT devices, and it's also great for synchronizing with cloud computing resources. But PTP might be used in industrial automation as an example, where we have an automated factory and robots and things have to be very precise. Or we might use PTP in audio-video broadcasting to synchronize up all of our streams. Or financial trading is another one. If you've heard of high-frequency trading, those traders often make their profit with very slight price variations in a stock, and the way they make their profit is by getting their order in before somebody else does. So these traders are very concerned about network delay and speed, and we have to have equipment that can see who got their order in first. And now that we've got a basic idea of when we would use Precision Time Protocol, let's consider how that synchronization happens. We said that the authoritative time source for a PTP domain was called the Grand Master Clock, and it can be pushing time out to an ordinary clock. And let's see how that ordinary clock can adjust its time to be in sync with the Grand Master Clock. Let's say that currently the time is 8 o'clock. 8 o'clock in 0 seconds. That's the official time according to the Grand Master. But if we were to look at the ordinary clock right now, it thinks the time is 8 o'clock in 30 seconds. So there is a 30-second offset. The big question is, though, how does that ordinary clock know that it should adjust its time by 30 seconds? Well, let's go through this. Periodically, the Grand Master Clock is going to send out sync messages. And we'll say that it sends out a sync message at exactly 8 o'clock in 0 seconds. Well, when that sync message arrives at the ordinary clock says, I just received a sync message, and according to my clock, the time is 8 o'clock and 31 seconds. And the ordinary clock is going to assign that to a value of T2. Now T1, that's the time according to the Grand Master that the sync message was sent. And some implementations of PTP will embed that T1 time in the sync message, but typically Cisco does something else. Instead of using a one-step sync, Cisco gear will typically use a two-step sync. In other words, it's going to follow up that sync message with a follow-up message that contains the value of T1. The Grand Master says, oh, by the way, that sync message you just got, I sent that, according to my clock, at 8 o'clock in 0 seconds. So now the ordinary clock knows that there is a 31-second disparity between the Grand Master clock and itself. Here's the challenge, though. The ordinary clock cannot just adjust its time by 31 seconds because part of that 31 seconds is the network delay, the time it took for those PTP packets to make it over to the ordinary clock. That means the ordinary clock needs to calculate two different values. It needs to calculate the delay value, the time it takes these PTP packets to cross the network, and it needs to calculate the offset, the amount by which it needs to adjust its clock. And it can do that mathematically, and we're going to walk through that math. We're going to have 4 variables. We already know 2 of them. We know that the Grand Master sent this sync message at 8 o'clock in 0 seconds. So that's T1. The ordinary clock received the sync message, according to the ordinary clock, at 8 o'clock and 31 seconds. But how do we get the values of T3 and T4? Well, the ordinary clock, after receiving the sync and follow-up messages, it's going to send a message of its own. It's going to send a delay request message over to the Grandmaster clock. And let's say that according to its clock, the ordinary clock says, I'm sending this delay request message at 8 o'clock and 32 seconds. And when the Grandmaster receives that, because another second has elapsed due to network delay, the Grandmaster clock's time is currently 8 o'clock and 3 seconds. And the Grandmaster will tell the ordinary clock, hey, you know that delay request you sent? Well, here in this delay response message, I want to let you know that I received that, according to my clock, at 8 o'clock and 3 seconds. We now know the value of our 4 variables. We know that according to the Grandmaster clock, it sent the sync message at T1, 8 o'clock, 0 seconds. The ordinary clock, according to its clock, received the sync message at T2, 8 o'clock and 31 seconds. That ordinary clock, according to its clock, sent the delay request message at 8 o'clock and 32 seconds. That's our T3 variable. And the Grandmaster received that delay request, according to its clock, at 8 o'clock and 3 seconds. That's T4. Now that we know all 4 of these values, we can simply plug and chug into our formula. First, let's do delay. And since everything begins with 8 o'clock and 0 minutes, we'll just use seconds in our formula. T2 is going to be 31 seconds. T1 is 0 seconds. We're going to take that quantity and add the quantity of T4 minus T3. Well, T4, that's 3 seconds, and T3, when the ordinary clock sent the delay request, that's 32 seconds, according to the ordinary clock's time. And 31 minus 0 is 31. And if we take 3 minus 32, we get negative 29. And we're adding these together. What is 31 plus negative 29? Well, that's the same thing as saying 31 minus 29, which is 2. And we say we're going to take that value of 2 and divide by 2, and that gives us the delay of 1 second, which is exactly what we see in our diagram. Now, obviously, in the real world, we are probably not going to have a delay of 1 second, but it makes it easy to visualize as we're going through the math. Now, let's calculate the offset. This is the amount by which the ordinary clock needs to adjust itself. Here, we're still calculating T2 minus T1, 31 minus 0, and we're still calculating T4 minus T3, 3 minus 32. But this time, instead of adding those quantities, we're going to say 31 minus negative 29. 31 minus negative 29 is the same thing as saying 31 plus 29, which is 60. What is 60 divided by 2? That's going to be 30 seconds. That is the offset. Our ordinary clock does this calculation and it realizes it needs to adjust its clock by turning itself back 30 seconds because it was running 30 seconds too fast. And then once it makes that adjustment, our clocks are finally in sync. They both agree that the current time is 8 o'clock and 6 seconds. And of course, network delay can vary on the network. That's why the Grandmaster clock is going to send out those sync messages periodically and will continually be adjusting our time. And here in this diagram, we've considered the Grandmaster clock and the ordinary clock. There are some other types. Let's define some of these different PTP clock types. First, as we've already discussed, the Grandmaster clock, that is the primary source of time in a precision time protocol domain. And this Grandmaster clock is often providing time out to ordinary clocks. And an ordinary clock is a PTP clock that's only running a PTP on one of its ports. And when we say a clock, we're talking about a network device, like a router or switch. In the Cisco world, we're primarily talking about a type of switch. And not every Cisco switch is going to support precision time protocol. Most switches would not have a need to do that, but we might see it in Cisco's industrial Ethernet line of switches. You might see PTP used on a Cisco Catalyst 9300 series switch as another example, but you're not going to find this on every single platform that you might have. Now, another type of clock we have is a boundary clock. Here, we can sit at the boundary of multiple PTP domains. That's as opposed to a transparent clock, which is going to be probably just a switch on the way from the Grandmaster clock to the ordinary clock that we're trying to sync up with. But we realize that when we go through a switch, as we go through this transparent clock, that is going to add some delay. After all, we're talking about accuracy on the order of nanoseconds. We need to measure that delay as we go through the transparent clock, and the transparent clock has the ability to measure that time. It's called the residence time. Something else to understand about the transparent clock versus the boundary clock is that a transparent clock can only communicate time on one VLAN. Whereas the boundary clock, sitting at the boundary of potentially multiple PTP domains, it can communicate time out to multiple VLANs. But let's focus on the transparent clock for a moment. We have a couple of types of transparent clocks, and on many of our Cisco switches that support PTP, the default PTP mode for that switch is going to be an end-to-end transparent clock. Here, let's say that we've got the Grandmaster clock on the left, we've got a transparent clock that we have to transit in the middle, and then we've got the ordinary clock on the right that we want to sync with the Grandmaster clock. Let's see how that synchronization happens. As we discussed earlier, the Grandmaster clock is going to send out a sync message, and there is some delay as we go over the path from the Grandmaster clock to that transparent clock. That's one path delay. Then the transparent clock has that ability to measure its residence time. How long does it take to go from the ingress port out the egress port on that switch? That's the residence time. And then that same sync message is going to be forwarded over to the ordinary clock. And we mentioned that Cisco typically uses a two-step sync where it sends a follow-up message saying, hey, by the way, T1 was this value. And then like we discussed before, the ordinary clock is going to respond with a delay request, and we won't go through the complete synchronization process, but then the Grandmaster clock would respond with a delay response. But the big takeaway for you is this. With end-to-end transparent clocks, that sync message goes all the way from the Grandmaster clock to the ordinary clock. That is as opposed to a peer-to-peer transparent clock. Here, the Grandmaster clock is going to send out the sync message to the transparent clock, and instead of forwarding that sync message, the transparent clock, after it receives the sync and the follow-up messages, it's going to respond with a P-delay request. It's wanting to determine the delay across that one path between the Grandmaster clock and the transparent clock. And it's going to calculate the residence time. How long does it take to go from the ingress port on the transparent clock to the egress port? And then the transparent clock is going to send a sync of its own. You see, it didn't forward the original sync over to the ordinary clock. It sent its own sync to the ordinary clock. And that path delay between the transparent clock and the ordinary clock, that was calculated independently. And then the ordinary clock can add up all of the path delays and the residence times to come up with the total network delay. But the big difference between the transparent and the peer-to-peer transparent clocks comes down to the sync message. The end-to-end transparent clock sends the sync message all the way through the network, but a peer-to-peer transparent clock responds to the sync message and then sends its own sync message to the next hop towards the destination. And for the Encore exam, we're not expected to know how to configure PTP. There are a lot of options. The exam blueprint says that we need to be able to interpret a PTP configuration, which is the reason we went through a discussion of those different modes in which a PTP clock can run. And the configuration and verification of PTP and the default settings, that might vary a bit depending on which Cisco device you're using. But in this example, let me show you the default configuration for a Cisco Industrial Ethernet or an IE4000 series switch. We can say show PTP clock. And notice that the PTP device type is end-to-end transparent clock. That's our default setting. But if we want to set this to a different PTP mode, we can go into global configuration mode and say PTP mode. And if we give some context-sensitive help, we see the different options available. We could say boundary to make this a boundary clock. We could set it back to end-to-end transparent if we wanted to. If we say forward, it's not really going to be acting as a PTP clock. It's just going to forward that PTP traffic through the switch without attempting to calculate a residence time. If we want to make a switch a Grandmaster, though, we can say GMC-BC, which is short for Grandmaster clock in boundary clock mode. And if I want to change this from end-to-end transparent to a boundary clock, I could say PTP mode boundary. And that's how simple it is to change to a different PTP mode. Now let's look at a couple of other examples. Let's say that we've got a Grandmaster clock and a boundary clock. If I say show PTP clock on both of these, if we look at the PTP device type on the Grandmaster clock, it says we're a Grandmaster clock. If we do that on the boundary clock, it tells us we're a boundary clock. Also, if we look a bit lower in the output, we can see that the offset in nanoseconds from the master clock is 0 on the Grandmaster clock because we are the master clock. And there is no path to have a delay, so the mean path delay is 0 nanoseconds, and the steps, in other words, the number of clock hops away from the Grandmaster we are, is 0 because we are the Grandmaster. If we look at the boundary clock, however, and let's pretend that this boundary clock is getting time directly from that Grandmaster clock, it might calculate that it has an offset of 17 nanoseconds from the Grandmaster clock. And we talked about how that offset was calculated. The mean path delay might be, for example, 12 nanoseconds. And since this boundary clock is 1 clock hop away from the Grandmaster clock, the steps removed is 1. And that's a look at the basic theory of precision time protocol and how we can interpret PTP configurations on our Cisco gear.